J-type profile or a build and hold profile. This is some features. It's, as you can see, it's simple. The kickoff point determines the inclination of the tangent section, and it has large horizontal displacements from a shallow kickoff point. Okay. So here is your kickoff point. This is your build section. This is the radius of the circle whose arc is your build section, and this is the end of build, and this is the tangent section. As you can see, the horizontal departure is large. So another modification of the build hold profile is the build. As you can see here, you have a first build section, and then you have a first hold or tangent section, and you have a second build section, and eventually you go horizontal, almost horizontal, let's say 88 to 90 degrees, and you hold that section again, second hold section. So you have a first build section, second hold section, a first tangent section, a second build section, and a second hold section. That's why it's called the build, hold profile. So it is recommended that the build-up rate for your first build section is less than the build-up rate for your second build section. So here is an S-well profile. So from build hold, and then hold, build hold profile, we have a S profile or a build, hold, and drop and hold profile. Okay. So the target is near vertical, and multiple target intersection may be possible. So it may be, as you can see here, it's not, you can finish off not vertical, or you can finish off vertical. So the directional control here is more difficult since you already built an angle here. You hold the angle, and then at some point at the drop off section, you drop the angle. Okay, so as you can see, there are again two circles here. So here you have your build-up rate to solve for R1, and here you have your drop-off rate to solve for R2. So as we have discussed previously, the torque and drag for this could be high because you have two bend section or build and drop section. The horizontal displacement for this one is limited since you're going to drop it somewhere at the end of your drop section. So these are some basic rules. So let's proceed here. So tip 1 for manual well planning, once you have determined the radius of the circle whose arc is your build section, you must draw a straight line from the center of the circle to your target. Okay, so now you have built here a triangle which you can analyze for your calculations. So as you can see here, you can also extend your radius right here, and you have an excess length in here. That is another triangle. Okay. So the idea of the manual well planning we are doing here is analyzing circular arcs and analyzing triangles. That's why you need your knowledge about trigonometry to analyze these lengths. Okay. So still tip 1 for J profile. As you can see, you have extended this line right here, and this arrow indicates that it has 180 degrees. Okay, so you can solve for the angle right here for this triangle. Just follow the cursor. And the angle, again, right here, which the arrow points to, this triangle where the cursor is. And eventually, you can just subtract that, both those angles from 180 degrees. So, to find this angle right here, the angle of your arc, of the arc of the circle, which is a fraction of the circumference of the circle. So tip 2, for a double build, if you have two build sections, the same thing. The center of each circle, right? Draw a straight line from each center. Okay, so now you build another triangle here, and it's just a matter of extending some other lines to build other triangles and find the angles. Tip 3 for S profile. So here, as you can see, the second circle would be a drop. The arc is dropping. Okay, so the circle is underneath your hold section or your tangent section. The same thing, draw a straight line from the center of the radius of the circle of your R1 to your R2 circle. So as you can see, you can generate triangles here that you can analyze for their lengths and for their angles. So tip 4, still for S profile, the same thing. Draw a straight line from the center of the circle, of the first circle, from your build section, and then to the center of the circle at your drop section, and you can extend this line here, which will be a right triangle. You can form a right triangle if you extend your line from here to there. It's like a projection of the center of the circle to this line right here. Okay, so you build a right triangle here. Okay, so these are just some tips how you can extend the lines, draw the lines, draw the circles, so that you can calculate the dimensions of your well profile. So this is a single J well. The first case is where the radius of curvature is less than the total horizontal departure. And the second case is the radius of curvature of the build section is larger than the horizontal departure. So for S, you also have here that the radius of curvature of your build section is way lesser than the total horizontal departure. And the second case is the radius of curvature is greater than the horizontal departure of your well. Okay, so here is our example. This is design of a 2D well. So we are given the following. So you only need some of this data, or as you can see, only 4 data. So design a directional well with the following restrictions, where the total horizontal departure is 4,500 feet, the true vertical depth is 12,500 feet, the depth to peak of point is 2,500 feet, and the rate of build of hold angle, or the BUR, is given as 1.5 degrees per 100 feet. So there's a hint here. This is a type 1 well, build and hold. So the required are determine the maximum hole angle or the inclination required for this well. And number 2, what is the total measured depth of the hole? Okay, so this will be the well profile for this 2D well that we are going to design. So as you can see here, the vertical section is 2,500 feet. So we need to build a J type well. So as you can see here, you will have a build from your tip of point. You will build your angle, and then At some point, you will stop building your angle. That's the end of build, and then you will just hold. You will drill straight up to your up to our target. So as you can see here, and if you will draw a straight line from target uh, to our origin, right here, if according to our given, it's 4,500 feet, the horizontal displacement or the total horizontal departure. Okay, so we know the kickoff point and the total horizontal departure, but we are being asked what is the maximum inclination and what would be the total measured depth for this well. So what would be the components of our measured depth? So of course, the 2,500 kickoff point is there. You have here this arc of a circle of radius 1 as your build section. And you have here the hypotenuse of this triangle right here with an angle given here as angle beta. And the angle right here is also equal to that angle. So if you extend this line, you can prove that the angle right here is the same as this beta angle, right? If you draw an intersecting line here. And since this is a 90 degrees and this is also 90 degree right here, we can conclude that this beta angle is also the same as this beta angle. And it so happens that this beta angle, the same angle of the arc of your build section, is the maximum inclination, as you can see here. Right? That's the maximum inclination of the tangent section or of this particular well that we are designing. Okay, so we also need to calculate the dimensions right here of this two true vertical depths, the TVD1 of your build section and TVD2 from the end of build up to the target. So we know that the total vertical depth is 12,500 feet. So the kickoff point is at 2,500 feet. So TVD1 plus TVD2 would be a total of 10,000 feet. So first thing is we need to know this arc, and according to our previous discussion, this arc is a function of the radius of curvature and this beta angle right here. So let's solve for the radius using our derived equation last time. So the build-up rate is given as 1.5 degrees per 100 feet. And this is the equation that we derived last time. Build-up rate is equal to 5,730 over the radius of curvature. Since we are given the build-up rate, we'll just manipulate this equation and solve for the radius of curvature. And that would be 5,730 divided by the build-up rate, 1.5. Our radius of curvature is approximately 3,820 feet. As you can see, our radius of curvature is smaller than our total horizontal departure. Okay, so let's follow the tip from before. From the center of the circle, whose arc is our measured depth 1, right here, we draw a straight line from it up to your target. So now we form this triangle right here, and we know that this is equal to your radius 1, right? As this is also your radius 1. And this is 4,500 feet. So as you can see, one side of this triangle that we drawn is the difference between our horizontal departure and our radius of curvature. So that would be 4,500 minus 3,820. And if you analyze this triangle to find this angle phi right here, according to our tip, we need to find this angle, right? In order to find the beta angle. that we are solving for. Also, we need to find this alpha angle right here. Okay? So this phi angle is the complement of the sigma angle right here. So this sigma angle, we can solve for the tangent of this angle is equal to the opposite side and divided by the adjacent side. You can see that. So that's 4,500 minus 3,820. Our horizontal departure minus the radius of curvature. That would be the opposite to this sigma angle right here, opposite side. So tangent of sigma is equal to 680 for 5 minus 3820 divided by the adjacent side, which happens to be 10,000 feet. So the tangent of sigma is equal to 0.068. So arc tangent of that is 3.89 approximately degrees. So to solve for angle phi, we just need, since it's sigma is a complement of it, we just subtract from 90 degrees. So 90 minus phi is 86.11 degrees approximately. So we have the hypotenuse of that same triangle. Why do we need that hypotenuse? Because we need to analyze the angle alpha right here, which is part of this total of 180 degrees. So we know phi angle. We want to know this beta angle right here. What we need is to give value to this alpha angle. So let's find the value for this hypotenuse right here, this y. So y is this, you just use Pythagorean theorem on this one. So y would be equal to the square root of 10,000 squared plus 680 squared, right? And that will give us approximately 10,023 feet. So we have a value for one side of this triangle, which is R1. We have a value also for its hypotenuse. We just solved it, 10,023 feet. So to find this angle here, we have a hypotenuse and an adjacent side. So we'll be using cosine. Cosine is equal to adjacent over hypotenuse. So cosine of alpha is R1, which we solved as 3820, and y, the hypotenuse, which we solved as 10,023. So our cosine of that value would give us the value for angle alpha, which is 67.59 degrees. So to find beta, we just need to subtract it from 180, the phi angle and the alpha angle. As you can see here, it's a total of 180 degrees. They are a part of a line with 180 degrees. So beta angle is 180 minus alpha minus phi, that would be 180 minus 86.11 minus 67.59. That gives us approximately 26.3 degrees value for our beta angle, or the angle of the arc of our measured depth 1, or the build section. Remember, we are looking for the maximum inclination and the total measured depth. And we divided the measured depth into components. First is the kick-off point, and then the measured depth of the build section, which happens to be an arc of a circle. We already derived the equation how to calculate the arc of a circle using the angle and the radius. And it's just a matter of analyzing the triangle remaining to find the measured depth 2, which is from the end of build up to our target. So we already have this angle right here. So it's just a matter of analyzing few triangles to do. So we already solved for the maximum inclination of the well, which is beta angle 26.3 degrees approximately. So that's 26.3 degrees. So we will be solving for TVD1. TVD1 is the vertical depth of our build section. This length right here is also equal to this length right here, which happens to be a side of this triangle right here, if you can follow the cursor. So we know that the hypotenuse of this triangle is R1, and we already solved this beta angle. So it's just a matter of manipulating trigonometric identities to solve for this side. And as we have a hypotenuse, an angle, and what we are solving for is the opposite side, so we'll be using sine. Sine is equal to opposite over hypotenuse. So TVD1 would just be equal to the sine of the beta angle, 26.3 degrees, multiplied by the radius of curvature that we have solved. So if you will plug that in your calculators, that's sine 26.3 degrees times 3820 feet. That would give us approximately 1692.5 feet. So that is for our TVD1. So for measured depth 1, we will just be using the circumference of a circle, the fraction of the circumference of a circle in terms of the angle. So using this equation right here for circumference, that's 2 pi r times the beta angle as a fraction of the total 360 degrees. Or we can cancel that 2 over 360, that is the same as 1 over 180, or pi, this, the pi here, pi over 180 degrees. So pi over 180 times our radius of curvature times our angle, that will give us the length of the arc of the circle. Okay, so plugging that in, we have MD1 as 1753.4 feet. So for MD2, we just need to analyze this remaining triangle right here. As you can see, MD2 is its hypotenuse. And we know the angle beta here. We know TVD2. Do we know TVD2? Yes, we do. Since this is 25, TVD1 is calculated as 1692.5 feet. So we just need to add this 2 right here, 25 plus 1692.5 feet, and subtract it from 10,000. So there, you have the one side of a of a what do you call this? Of a right triangle. Okay, so let's proceed. So measure depth 2, tangent of this alpha angle right here. Let's go to this triangle. Tangent of this alpha. Here's another way to find measure depth 2. The tangent of this alpha angle right here is the opposite over the adjacent side. The adjacent side is R1. This is the first thing that we have calculated. We have a value for alpha angle, that is 67.59. So that would be tangent of the angle is equal to the opposite over the adjacent side. So tangent is equal to opposite. Therefore, we need to multiply our adjacent side to the tangent of the angle. That's why tangent 67.59 times 3820 feet, and that gives us the length for measure depth 2 as 9263 feet. So doing the math, so we have 2,500 from our surface to kickoff point. The arc or the measure depth 1 is 1753.4 feet. And measure depth 2 is 9263.4 feet. And that gives us a total of 13,516.8 feet. This is our total measured depth. This would be the total length of our drill string, and of course the casing string. That's 13,516.8 feet. That's the total measured depth for this 2D well, J-type, with our given restrictions. And remember that the maximum inclination is the angle beta, which is 26.3 degrees. An alternative way to calculate for the maximum inclination is with this equation right here. But the tricky part here is you need to identify the lengths at first. So you know that the TVD from the end of build up to your target is TVD2. The TVD from your kickoff point to your end of build is TVD1. Okay, so don't interchange it or you will result in a wrong value. We have here horizontal departure 1 is the horizontal departure of your end of build. Horizontal departure 2 would be your horizontal departure 2 would be the difference between your R1 and the horizontal departure 1, or the difference between your radius of curvature and the horizontal departure of your end of build. While horizontal departure 4 is the total horizontal departure, it is given. Horizontal departure 3 is the difference between your horizontal departure 4 and horizontal departure 1. The total horizontal departure minus the horizontal departure of your end of build section. Okay, so if you are able to identify those lengths, you can plug it in this equation right here. Okay, HD4 squared plus TVD2 minus TVD1 squared minus 2 times R1 plus R2. So as you can see, you can use this for your J-type well as well. S-type well. You have R1 and R2. But in our case, we don't have an R2 since this is a J-type well. That's why R2 here would just be equal to 0. As you can see here, R1, the value for R1 plus R2 is just 3820 or equal to our R1. So solving that equation will give us the value for the angle here for the arc of a circle, or the same angle right here, which is the maximum inclination of our J-type well. So 3D trajectory planning, as I have mentioned before, we will be just studying minimum curvature or circular arc method. So it fits the well path on the surface of a sphere of a particular radius. So use a method similar to radius of curvature and is the preferred method for horizontal lines. So as you can see here, we introduce DL, or what we call the dogleg severity. As you can see, the dogleg severity is just the angle, the same as your build-up rate. Okay? The same as your build-up rate, but it involves changes in inclination and azimuth. Okay? So as we defined our build-up rate before, we assume that there is no change in azimuth, and we said that the value calculated for that equation would just be equal to the dogleg severity, which is also in degrees per 100 feet. So this is the total dogleg angle, the total change in whole angle between two survey points involving changes in inclination and azimuth. So this beta angle or dogleg angle is equal to twice the arc sine of the square root of sine squared of the change in inclination over 2 plus sine squared of the change in azimuth over 2 times sine I1 and sine I2. That will give you the dogleg angle. So the dogleg angle, in order for you to convert it in as dogleg severity, remember, you are solving for the angle here. Dogleg severity would be in degrees per 100 feet. So you have to multiply your answer by 100 so that you will get degrees per 100 feet. This is API Bulletin D20, this equation. So we have an example here. We have two survey points, survey 1 and survey 2. This is the data. So the inclination at survey 1 is 20 degrees. The azimuth is 70 degrees. And the measured depth at survey point 1 is 10,200 feet. At point 2, The inclination increased to 30 degrees and the azimuth increased to 130 degrees. So as you can picture, we are moving on a clockwise direction. We are turning on a clockwise direction. So the changes are I2 minus I1, that's 10 degrees, and A2 minus A1, that's 60 degrees, and the change in measured depth is MD2 is 10,350 feet. So just subtract that, and the change in measured depth is 150 feet. So let's plug that in on our equation to calculate the dogleg angle. So as you can see here, the calculation of the dogleg angle, three-dimensional, we just plugged in the values here. So we have sine squared 10 over 2 plus sine squared 60 over 20 times sine 20 sine 30. So plugging that value, we have 25.93 degrees. That is the dogleg angle. Okay, so solving for dogleg severity, it's the same as solving for your build-up rate and your turn rate. So how do we solve for build-up rate? We divide it by the course length or the change in measured depth, and then we multiply it by 100 feet over 100 feet, so that we will get a unit of degrees per 100 feet. Okay? So our dogleg angle times 100 divided by 150. That gives us the dogleg severity of 17.29 degrees per 100 feet. Okay? So remember, the dogleg angle would be different from your dogleg severity. So the dogleg severity, you need to divide it by the course length and multiply it by 100 since you are measuring degrees per 100 feet. So the first equation from API Bulletin D20 that we introduced is solving for the dogleg angle.